Hi, students. Let's continue lecture 4. The circuit analysis. For the previous lecture, I'll talk about our transmission line and also show you some examples, also problems. Let's continue with the transmission line theory. And as you know, this is the transmission line circuit network. Let's take a look at it more deeply in the term of the voltage and the current. That's the time and x dependent. Let's set up the voltage along the transmission line to be xt, and that are equal to a exponential negative gamma x plus b exponential gamma x, and in the time domain we add exponential j omega t, same as the current. Okay, but they have a different coefficient. That's going to be c and d. They're both constants. I'm not going to prove the relation between the voltage and the current. Simply apply KVL and KCL, Kirchhoff voltage law and Kirchhoff current law, and thus your current is going to relate it to the voltage in a similar form, but you have a negative sign in front of constant B. Now take a look at the two terms for the voltage along the transmission line at arbitrary times and x. The first term, exponential a exponential negative gamma x, simply is the incoming signal or the forward signal. Sometimes we put that as the VF, subscript F. And for b exponential gamma x, that's the become reflected signal from the load line or the load end, and or sometimes we call it backward voltage VB. Okay, and you can explain for the current in similar point. Now you also remind you that for your characteristic impedance in unit of ohms, your Z0 related to the distributed parameters prime, L prime, T prime, C primes in this form, as well as your propagation constant. Your gamma simply become the real part plus the imaginary part. For the real part, that's the attenuation constant in the unit of our neighbor per meter. And for beta, that's the phase constant in the unit of radian per meter. You can see that when the signal going through the transmission line or going along the transmission line, your phase is going to be different, because this is the unit in the radian per meter. And your propagation constant also can be written in this form in the term of distributed parameters. Okay, just that remind you before we move on. Now let's take a look at special cases. For open circuit termination, this means you have an open circuit at the load end, or your ZL, you have no load at the end of transmission line, or your impedance simply is going to infinity. So you put this one as on the most left at the source of the transmission line. You put this one as x equal to negative L, where L is the length of the transmission line, and at this point x equal to 0 at the load end. Well, we already make agreement that your voltage simply equal to Vf plus the Vb, or the forward voltage plus the backward voltage, or reflected voltage from the load. For your the source impedance of the open circuit, put this one as Z as 0. That's equal to like the input impedance. So that's equal to V over I according to Ohm's law, at X equal to negative L. And for the current, since this is open circuit termination, so you have no current flowing through the load, so your I at negative L equal to 0, along the transmission line. Since your I equal to the forward current plus the backward current, you end up with A equal to B. This is just only about the math, because you know that your current is what? In the term, okay? A exponential negative gamma t minus B exponential negative gamma t divided by Z0. And you put, sorry, I put this one is wrong, supposed to be X, my mistake. So you put X equal to 0, you end up with A exponential to the power of 0 minus B exponential to the power of 0 divided by Z0. You end up with A equal to B. So your source impedance, the open circuit, turn out to be this term at their source. And the relation, this end up to be a cotangent of gamma L. And you also put A equal to B. Now for gamma L much less than 1, you know that cotangent gamma L, that's approximately 1 over gamma L. And since you have the source impedance Z is 0 equal to Z0 over gamma L, because you just plug in there, this is your Z is 0 equal to Z0 cotangent gamma L, and your 0 for the lossless line, lossless transmission line, you know that Z0 equal to square root of L prime over C prime, and your cotangent gamma L, where gamma L much less than 1, that's equal to 1 over gamma L. You just plug in the cotangent of your gamma L to be 1 over gamma L. That's why you have this term here. Same for lossless transmission line. Your gamma, it was written here, where R prime and G prime is about 0, so you end up with J omega square root L prime C prime. Okay, so that's why you have J omega square root L prime C prime here, and L, which is the length of the transmission line. And I make a note here for a lossless transmission line. G is about approximately 0, same as R. So you work this out, you end up with Z is 0 equal to negative J over omega CL. Alright, we're going to use this term later on. That's for open circuit termination. Next, for the special case, that's the shorted circuit termination when you short the circuit at the load end, or your ZL equal to 0. At this point, this means that your V0 equal to 0, right? Because it's shorted to ground. And from the voltage equation, you have a Vxt equal to this term. So you simply put x equal to 0, 0, and make Vxt equal to 0, because this is the shorted circuit to the ground. So you end up with A equal to negative B. That's why I have A equal to negative B here. Now you look at the source. Your impedance at the source end on ZSS, that's equal to V over at x equal to negative L divided by I at x equal to negative L. And this one end up with Z0 tangent of hyperbolic tan of gamma L. For gamma L much less than 1, your hyperbolic tan gamma L approximately gamma L. Okay, so you end up with the source impedance for the shorted circuit termination equal to Z0 multiplied by gamma L. Just pick up this equation here, because your hyperbolic tan or gamma L is approximately gamma L. For the lossless line, you know Z0 equal to square root L prime over C prime, and then you multiply by gamma L. This is your gamma for the lossless line. So you end up with the impedance of the shorted circuit termination equal to J omega L prime multiplied by L. So don't get confused. You know, I put this one as L, the uppercase L, but the L prime simply is the distributed parameters, or the inductance. But this one L here is the length of the transmission line. Next, for arbitrary termination impedance, for your ZL not equal to 0, neither ZL not equal to infinity. So you just work straightforward. At the load end, your ZL is simply equal to VOI for x. You put x equal to 0 according to Ohm's law. This is a little bit more complicated. You can work out. It's only math. You get the ratio B over A equal to ZL minus Z0 over ZL plus Z0. I put this one as P. And for the source end, you end up with this term. We just work straightforward. And if you are substitute B over A, because you have A and B here constants here, right? You get rid of B and A by using whatever you have in the circuit, which are the load impedance and the characteristic impedance. Finally, you have your source impedance equal to Z0. That's the characteristic impedance. multiplied by ZL plus Z0, 10 gamma L divided by Z0 plus ZL, 10 gamma L. Okay, and that's for arbitrary termination impedance. And what I don't have here is that for the match impedance, matching impedance, you have a ZL equal to Z0. So your ratio B over A equal to 0. That's what we are looking for, because you don't want to have any reflection from the load end. And that that's what we call the match transmission line, when your ZL equal to Z0. Take a look at the problem 3.9, page 100. For the open-ended transmission line, or open circuit termination, all parameters are given as you define the source impedance of the open-ended transmission line. Well, you just plug in the number into negative J over omega C prime L prime. This is the input impedance for the open-ended transmission line. Problem 3.10, page 100. From the previous problem 3.9, Vs equal to 4 volt. This is simply the AC signal as you define the current. So the current simply become Vs over Z, since you already worked out for Z, the input impedance from the previous problem, right? That's for the magnitude, that's the 530.52 ohms. So you simply divide the voltage by the input impedance. So you end up with the current is 7.5 milliamp. For the problem 3.11, page 100, talking about shorted end transmission line. For the length of the transmission line is given 14 inches. As you define your current, so what you need to do, because the voltage given, that's the 3 volt, so you are looking for the source impedance of a shorted end transmission line, and this is your shorted impedance, the source impedance, that's the J omega L prime L. Okay, this is just like straightforward. So you end up with the current. You divided the voltage source 3 volt by the input impedance, that's the 3.67 10 to negative 4th ohms. Problem 3.12, page 100. As you define the signal velocity along the transmission line, so you know that for the lossless line, we talked about it before, the signal velocity along the transmission line are simply equal to 1 over square root L prime C prime. Okay, and L prime given, C prime given, so you end up with the signal velocity 1.99 10 to 12 meter per second. Okay, so that's our for the transmission line theory. to get into the shorted termination and the open layer termination, as well as the arbitrary load termination. Okay, that's what I have here. Next, a problem again with okay, that's better. Now take a look at example problem 3.13, page 100. The source impedance given equal to characteristic impedance Z0, that's 50 ohms, and you have the source voltage 3 volt. Determine a forward voltage and current when the switch is closed. Okay, this is the first thing you need to do a voltage divider just to see what is the input voltage into the transmission line. This is just only the source, the voltage source. So you need to consider what is the input voltage through the transmission line. You simply apply a voltage divider that's equal to VA's, okay, that's the source voltage, multiplied by the characteristic impedance, and then divided by a characteristic impedance plus your source impedance, ZS. So you have the input voltage simply is become 1.5 volt instead of 3 volt, and of course the forward current equal to FO was Z0, and you have the forward current become 0.03 amp. Now you take a look at the load end. You see R equal to 30 ohms. Determine the backward voltage VB and the backward current IB. Where you have an incoming voltage or the forward voltage, since your ZL not equal to Z0, so you have the what's that? You have a deflection. So your reflection coefficient, that's the at the load end, equal to ZL minus Z0 characteristic impedance divided by ZL plus Z0, and that end up with your deflection coefficient to be a negative 0.25. Since the transmission coefficient, reflection coefficient actually equal to the backward voltage divided by forward voltage, or VB divided by VF, you end up with VB equal to negative 0.375. As you can see from this equation, the reflection coefficient TL at the load line. In case ZL equal to Z0, this turn out to be 0, so you have no reflection, or your backward voltage going to be 0, right? Same as the backward current, IB simply equal to tau L IF. You already have a tau L. Deflection coefficient at the load end, that's the negative 1/4. So you simply multiply by the forward current, that's 0.03 amps. You end up with the backward current to be a negative 7.5 milliamp. Okay, let's wrap up with problem 3.14, page 100. Hold on a second. Okay, for problem 3.14, page 100. Ask you to construct a reflection or lattice diagram. This is your reflection or lattice diagram. For the vertical x-axis. This is the point along the transmission line, where the horizontal one, right? For the vertical one, from the top to the bottom, that's the time. You can see the time increase from t0 to t, the uppercase T. That's the period. This means the time for the signal from the source to reach the load. Let's take t seconds. And of course, you can look for the time simply equal to the length of the line divided by the velocity of the signal velocity along the transmission line. And Vp is given, that's 2 nanoseconds per feet. As you were to draw the lattice diagram, well, first you have the load impedance, that's 30 ohms, then the characteristic impedance, that's 50 ohms. So you have the reflection coefficient at the source equal to Zs, that's the source impedance, minus Z0, that's the characteristic impedance of the transmission line, divided by Zs plus Z0. Since there's Z0 equal to Zs, so your transmission coefficient turn out to be 0, or you mesh impedance at the source end. Now for the load end, you tau L equal to the load impedance ZL minus characteristic impedance divided by ZL plus C0. You end up with negative 1/4. Now let's take a look. When you send signal through the transmission line, at the time t0, your signal will go along the transmission line, and let's take the time t. Okay, and then that signal will reflect it back, because you have a reflection coefficient that's not equal to 0. You have that equal to negative 1/4. So at this point, you have I put the number 1, 2, 3, 4, 5 just there to be clear, to take a look what is the total voltage at each arbitrary time. So your T1 simply become Vin, that's also a voltage divider. Your source voltage 3 volt here, and your characteristic impedance is 50 ohms, and your source impedance is 50 ohms. So you have Vin, that's the input to the transmission line, is the 1.5 volt instead of a 3 volt. We work out a problem like this before, previous problems. Number 2, you have V2, because this is the input voltage is reflected back from the load to the source. So you simply multiply Vin, that's 1.5, by the reflection coefficient TL at the load end, that's negative 1/4. And for V3, you also have a signal, like signal from that's reflected back from the load to the source, and also reflected back from the source to the load. But since you have no reflection at the source end, so your V3 is still equal to V2. Okay. Now for T equal to 3T, the signal from the source to the load on the line number 3 also reflected back to the source, and you need to multiply by tau L. I mean V3 multiplied by tau L, which is tau L is negative 0.04. Okay, so that's the idea, how you can see what is the total, like the voltage, because you have incoming. You take a look at the load N, you have incoming signal, and you have outgoing signal, or you have a forward voltage and the backward voltage. You just add them up, depending what time you're looking at. You look at T to 3T, 4T, and 5T. Okay, that's all for the lecture number 2. Lecture number 4, series 2.